Mauricio Bustamante. So Mauricio is an assistant professor at the Niels Bohr Institute at the University of Copenhagen. And his expertise is in high energy astroparticle physics and especially in high energy neutrinos. He has been building theoretical models and predictions for astrophysical multi-messenger sources, and also has been analyzing IceCube neutrino data. So also he's one of the pillars of the GRAND project, the Ultra Energy Neutrino Detection Project, and one of the collaboration board members, and he is actively contributing to shaping up the project. So, but his background is from particle physics, and he's also been devoting part of his research to fundamental particle physics. And he has recently obtained a Willem Young Investigator Award, with which he founded his thriving group at NBI. And today he's going to talk about the future today and the future of astroparticle physics. Thanks, Mauricio.
Thank you, Kumiko. Thank you, everybody, for being here. Thanks to the young people for being here as well. It's a very welcome surprise. So yes, I'm going to talk about today and the future. And let me start with something close to us. So as human beings, when we see a flower, we see it in the optical wavelengths. But if we were a bee, we would see detail that is not there. And a similar thing happens when we look at the universe with different eyes. So we use optical light, we see some structures in the galaxy, we can move on to radio waves and see things that we didn't see before, infrared, X-rays, gamma rays, and we can look at the universe in non-electromagnetic eyes with a new kind of messenger at the very highest energies. And that messenger, as you can probably guess, are neutrinos. What you're seeing there is 6 years worth of IceCube. IceCube is the largest neutrino telescope at the highest energies we have today. And it's pointing towards a new window to the universe, not only for astrophysics, but also for particle physics. So for 100 or so years so far, we have used increasingly powerful accelerators to find new particles, new interactions between them, and new underlying symmetries, and we build the standard model on top of that. Today, these accelerators still churn out valuable data, but so far have failed to significantly guide us to further significantly our view of fundamental physics. So we can go to higher energies and to these astrophysical environments that make energy particles at energies that otherwise would be unreachable, and in particular look at neutrinos to test particle physics and high energy astrophysics in ways we could not do before. So I'm going to build up from the beginning and then slowly but surely lead you to what we can do today and what we can do in the future with more data, more detectors with the highest energy neutrinos. But let me start at the very beginning. Neutrinos are elementary particles that are electrically neutral. They're very light and they're superbly antisocial. So they're so light that we don't know how light they are. They are so antisocial that typically they don't interact. There's a caveat there. When the energies of the neutrinos are very high, they do interact, and that is important. And I'll come back to that later. Not only that, they're quintessential quantum particles. Neutrinos come in 3 types or flavors, and we call them electroneutrinos when they're associated to an electron, mu neutrinos when they're associated to a muon, or tau neutrinos when they're associated to a tau. So they have different properties depending on which is the charge lepton they're associated to. But the interesting thing is that we learned in the past few decades by looking at atmospheric neutrinos, reactor neutrinos, accelerator neutrinos, et cetera, that a neutrino created once with one flavor won't stay necessarily with that flavor later. We call that phenomenon neutrino oscillations, that it becomes also important at the highest energies in astrophysical neutrinos. So a neutrino, as I said, created with a new E flavor, for instance, could be detected as an electroneutrino or a mu neutrino or a tau neutrino down the line. That probability depends on the energy, on the distance traveled, and some constants of nature as well. Very well. So these flavor oscillations have been important. They have received a couple of Nobel Prizes. They're pretty well understood to an extent, and they bring us also information about what the astrophysics of these processes at the highest energies that could make these neutrinos could look like. Very well. So I like this because this is an instance where quantum mechanics works on macroscopic distances. So essentially, this is interferometry, or interference, I should say, at distances that can go up to gigaparsec scales. Okay, so neutrinos have interesting properties, and not only that, they are ubiquitous. So they come from the fission products of reactors, from the crust and the mantle of the Earth, where radioactive elements decay and give us mainly thorium and uranium, and give us neutrinos. From the sun, from the fission reaction, like supernova remnants, and from the very farthest reaches of the universe, in things like supermassive black holes, like the one you see here, that are spewing matter out in collimated jets that go at relativistic speeds. In particular, this is a blazar. And those are the neutrinos that have the highest energies, and that will be the subject of what I'm going to say later on. Okay, so that was more or less as a way of graphical introduction, but let me be a bit more specific. If we have a plot of neutrino energies in the x-axis and distance from the sources to us in the y-axis, we'll see where these very high energy astrophysical neutrinos sit. On the bottom left, so at the lowest energies and at the shortest distances, are all the neutrino sources that we have used through the decades to learn the most about neutrinos. So for instance, there's the geoneutrinos from the Earth that I was talking about. There's the reactor neutrinos, the neutrinos from the sun at a bit longer distances, so order of 50 kiloparsecs or so, are a galactic supernova, maybe farther away if we're lucky. And just as a point of comparison, this is 1 parsec. The closest exoplanet, I know there's people working on exoplanets here, is roughly at this distance. But the neutrinos that we're interested in for today are on the opposite end of that plot. So these are the neutrinos that have the highest energies that we've seen so far. Not only that, they have the highest energies that we might ever see, for neutrinos at least. And they travel the longest distances, essentially up to the size of the observable universe, the gigaparsec scale distances from their sources to the Earth. So those two fundamental reasons are why these neutrinos are interesting. The highest energies allow us to probe energy scales that are far from the reach of accelerator experiments, and also allow us to probe non-thermal sources at the extreme energies of the universe. And the long distances allow us to see very far away, but also for particle physics, it means that even if we're looking for very small new effects that would be individually tiny, during a very long trip, these effects can accumulate over the span of gigaparsec scale distances and become observable by the time that the neutrinos reach the Earth, and therefore may be detectable at the Earth. So those are the two fundamental reasons why it's interesting to look at these very high neutrinos. The practical reasons is that in the next years, say 10, 20 years, there's a host of experiments across several orders of magnitude in energy that are going to be built and that are currently being either built now or planned for. And you see that they span all the way from 10 to the 5 electron volts to the absolute highest energies of 10 to the 21 electron volts. So at the lowest energies, I'm not going to talk much about that, but these are the experiments about from which we learn about oscillations the most. And there's some interesting synergies between what we can do with these very high neutrinos and what we have learned with these lower energy neutrinos. But what we're talking about today are these two blue and red regions over here. So they have what I call high energy neutrinos go from TeV, 10 to the 12 electron volts, and that is roughly the kinetic energy of a flying mosquito, all the way to roughly tens of PeV. And those have been discovered in 2013 by the IceCube Neutrino Telescope. And today we're gathering more statistics and trying to find more about these neutrinos. But there's neutrinos that have 1,000 times higher energy. They were predicted roughly 60 years ago at this point. We've been looking for them. Their flux is very low, so we haven't seen them yet. But there are new experiments and new techniques that aim to discover these ultra-high energy neutrinos in the next few years. So motivated by this, I will present things along two science thrusts. The first one speaks to what we have today, so about TeV to PeV neutrinos. So again, 10 to the 12 to 10 to 15 electron volt neutrinos. And the other one speaks to the next decade or next couple of decades on neutrino physics and energies 100 or 1,000 times higher, which we don't have today, but we might have later. Okay, there's one more thing here. This is a talk about astroparticle physics. And because this is astroparticle physics, there's two sides of the coin. On the one side, we use these observations of neutrinos in this case, but also if we want to be broader, of gamma rays and cosmic rays, and we try to make sense of them and learn about the highest energy sources like the one I'm showing there. On the opposite side of the coin, we reuse those informations and learn about particle physics. And there's a host of different things we can do. And I'll flash a few. You might recognize some of them, like neutrino-nucleon interactions, neutrino-neutrino interactions, which, as you can imagine, are very feeble, and a host of different things involving dark matter, neutrino decay, dark matter decay into neutrinos, new interactions of neutrinos with matter, breaking of fundamental symmetries of nature, like Lorentz invariance, and maybe there's more than 3 neutrinos over there, and they can mix with the active ones. So because this is a nascent field, there's much that we do not know about both the astrophysics and the particle physics that we can do with neutrinos at the highest energy. So every observation we do is essentially an observation that tells us about both, brings us information about both of them at the same time. In other words, if you're a Bayesian here, the prior on both the astrophysics and the particle physics sides are so wide that every observation you do is shrinking the posterior, both in the astrophysics side and the particle physics side. So it's an exciting time to make progress in this direction in both sides. All right, so let me first talk to you about what's been going on and where we are today. And for that, I need to introduce a bit of a technical thing, and that is, how do we make neutrinos at the highest energies? And this is just a toy model. We believe that the sources of neutrinos are cosmic accelerators. So think about very luminous supernova, active galactic nuclei, starburst galaxies that are able to trap protons and other charged nuclei and slowly accelerate them by a Fermi acceleration, maybe, so crossing a shock front multiple times, up to 10 to the 20 or 10 to the 21 electron volts. And these protons eventually have a power law-like spectrum, like energy to the power of -2. So they're pretty, that's the expectation. And the sources, those high energy non-thermal protons will interact with either ambient radiation, so photons, or ambient matter. And in both cases, they will create intermediate pions. And those pions quickly decay. The pi zeros, the neutral pions, decay into gamma rays, which add to the gamma ray emission from whatever source we're thinking about. And the pi pluses, there are also pi minuses that I haven't written there, decay and give you neutrinos at energies that are very high. So they take a big fraction of the parent proton energy. And I'm gonna say how much in a moment. As you see, sometimes we get final state neutrons. The neutrons, of course, are no longer magnetically confined at the sources, so they escape and they beta decay outside the sources on their way to Earth. And those protons that they make add to the ultra high energy cosmic ray observations that we have been collecting over decades. So these 3 particles are linked in a network of production processes, neutrinos, gamma rays, and cosmic rays, and their energetics are also linked. So each of the final state neutrinos that we're making here takes about 5% of the parent proton energy, and the gamma rays take about 10%. The full picture comes from examining all these messengers at the same time. But for the purpose of most of my talk, I will mainly focus on neutrinos, and then occasionally I will actually touch upon the other messengers. One thing that I want to point out is I was talking about flavors earlier, and upon decaying, these pions make roughly 2 mu neutrinos per each electron neutrino. I say roughly because there's other processes going on. And this will become a bit important later. So remember that neutrinos are produced with some flavor composition initially, 2 mu neutrinos per 1 electron neutrino. All right, so this toy model of neutrino production can happen in multiple places. We have the Earth here. There's a distribution of sources. Let's just not specify what the sources are for now. And distributed from the local universe all the way to redshifts of, let's say, 4 or 5. Contributions from farther away don't matter much. So inside the sources, we can have protons that are trapped with energies of tens of PeV that are making neutrinos with energies of up to PeV scale. And those are the contribution of all the sources making those neutrinos are the ones that IceCube discovered in 2013. Those are the high energy astrophysical neutrinos. So those are seen. What are not seen are the neutrinos that we believe are made by protons that have 1,000 times higher energies. So those protons could, again, interact inside the sources and make neutrinos now at 1,000 times higher energy, so 1,000 PeV or 1 eV, 10 to the 18 electron volts. We call them ultra high energy neutrinos. And that can happen inside the source by the process of proton-photon interactions or proton-proton interactions. But it can also happen if these sources are emitting cosmic rays, and the cosmic rays interact with the photons of the cosmic microwave background along the way to the Earth. So a cosmic ray comes out, interacts somewhere along the way with a photon of the CMB, and undergoes the same photo production process and makes, again, a neutrino with 1,000 PeV of energy, 1 eV of energy. And those ultra-high neutrinos we have not seen, but they are the target of next generation experiments. Let's see what we do know today. So what do we know about this TeV to PeV high energy astrophysical neutrinos? And when we talk about neutrino detection, this is a bit of an odd, I was just talking to the students. It's odd that we need to build these things at special spots on the Earth. So if you're a normal astronomer, you go as high as you can to build your telescope. If you're a neutrino astronomer, you go as deep as you can to build your telescope. And that's because there is a background of neutrinos and other particles that are made in the atmosphere, not in the astrophysical sources, that may mimic the signal made by astrophysical neutrinos in the detector. So you want to go as deep as possible in order to shield your detector from that atmospheric neutrino and muon background. So what I'm referring to is that sometimes a proton will come into this, I should say all the time, protons are coming into the atmosphere, interacting with an ambient proton and creating a particle shower. The particle shower develops as the particles travel downwards all the way to ground level. And by the time that they reach ground level, it's mostly made up of muons and neutrinos. So these neutrinos are atmospheric neutrinos, and we do detect them. We have been building detectors to see them for years. And the muons that are dealing with these muon neutrinos are the background that we need to shield our detectors from. So whereas neutrinos will just go through 1 kilometer or 2 kilometers of dirt on top of the detector, muons will get stopped, mostly, not completely. And therefore, you at least kill that background of atmospheric muons. That's what you build it. Very well. So that's been the strategy for years. And at the highest energies, we have, more or less today, 3 detectors, 3 neutrino telescopes. We have, until very recently, Antares in the Mediterranean Sea, the Baikal detector in Lake Baikal in Russia, and IceCube very near the South Pole in Antarctica. And I will say more about what's going on with these 2 in a moment. But IceCube is so far the biggest one and the only one that has detected the flux of TeV to PeV astrophysical neutrinos. It is a Cherenkov detector built, as I said, very close to the South Pole, and it consists of 1 cubic kilometer of Antarctic ice instrumented with photomultipliers, about 5,000 of them, buried between 1.5 kilometers and 2.5 kilometers. And what happens, this is one of them, by the way. So what happens is when a neutrino comes in, it will interact with the ice, then proton or a neutron. It will create a particle shower of about 10 meters in size. Yeah, and then the charged particles inside that shower are traveling faster than the speed of light in the ice, radiate Cherenkov radiation that propagates through the ice and gets picked up by the photomultipliers. So the size of the light profile is hundreds of meters, whereas the size of the shower itself is only 10 meters. The light propagates farther, of course. And depending on what is the character or the flavor of the neutrino that interacts, we have, roughly speaking, 2 broad classes of light events that the telescope detects. We have showers, which are roughly spherical light profiles. So a neutrino came in from some direction, interacted in the deep center of this blob, and then outwards emitted the light that propagated and hit the photomultiplier spheres along the strings. And that's why you see these little blobs. The closer you get to the center, the more light it is, and it's been expanding from the center outwards. These can be made by nu E and nu tau, mostly. And when it's a new mu, the other flavor of neutrino interacting, what happens is that on top of that shower, you had a neutrino coming in, interacted here, created a shower, and out came a final state muon. This is a charge current interaction for those that do particle physics. And then that muon left a track of Cherenkov light in its wake, which is what you see here. So this is very good for pointing because you have a leverage arm that allows you to point in the original direction of the incoming neutrino, whereas this is not really good for pointing. At 10 degrees of resolution versus 1 degree is a big change. Very well. So from these 2 kinds of events, plus other ones that are more specific, IceCube roughly has 4 observables that they work with. They're the energy spectrum, that is how many neutrinos per energy interval we have. the arrival directions of the neutrinos, the flavor composition, so how many neutrinos of each of the 3 flavors we have at the detector, and the timing information. And that mainly refers to the possibility of having a transient astrophysical source making gamma rays and neutrinos at the same time, and seeing if there's any difference in their arrival times at the Earth. So we have standard expectations for all 4 of these observables. As you can see there, we expect like something like a power law energy spectrum for the neutrinos. I'll say more about this in a moment. We expect that if the sources are distributed isotropically in the sky, the arrival direction of the neutrinos into the detector should also be isotropic. And as I said, we expect the neutrino flavor composition at the Earth after neutrinos have oscillated along the way to be more or less equal amount of each flavor at the Earth, or equal amount of nu mu and nu tau. And as I said, here for arrival times, we expect equal or similar arrival times from neutrinos and gamma rays from transient multi-messenger sources. All right, so let me show you a bit of data. And this is after about 8 years of IceCube collecting the most astrophysically pure sample that they report. It's called the High Energy Starting Event Sample, HESI sample. They have about 100 events of them where the neutrino interacted inside this cubic kilometer of ice. They have hundreds of thousands where the neutrino interacted outside, but this is the most astrophysically clean one. As you can see, these are the data points. This is the number of events in the y-axis, and this is the deposited energy of the event in the x-axis. These are data. These 2 in purple and red are backgrounds from the atmospheric neutrinos and muons that I was showing earlier. And in yellow, what you have is the astrophysical component of neutrinos that you need to add in order to explain the data. Without this yellow component, you don't fit the data points. That detection of astrophysical neutrinos is now at something like 8 sigma or maybe more, so it's really there. There's also information for the arrival directions. I'm just showing information from the NG spectrum. And as you can see, the neutrinos reach something like a few PeV, maybe 10 PeV. That's the highest we go. It is the neutrino spectrum, so the number of events per energy interval is very well described by a power law, e to the power of something, minus something, because there are fewer neutrinos at higher energies. And when one fits the normalization of that power law and the spectral index, so the tilt to the data, if you look at the blue blob over here, one actually finds that the value of the spectral index is about 2.9, which is pretty steep. Remember back a few slides ago, I said that the neutrinos are made by protons that have an e to the -2 spectrum, but these neutrinos are actually showing something that is closer to e to the -3. So there's some tension over there, but the tension is actually not super significant statistically. If in fact, if you use other data sets, not the ones represented here, but all the data sets reported by IceCube, you actually get a fit to the spectral index that is closer to 2 and a bit better compared to our theoretical expectations. Very well. So today, what we have is roughly this. This is a plot of neutrino energy in the x-axis, flux multiplied by 2 powers of the neutrino energy in the y-axis. And it's a power law with some tilt, and the tilt depends on exactly what IceCube data set we're using. I'm just showing 2 of them there. It's somewhere between e to the power of -2.3 and e to the power of -2.9, somewhere in between. All right. What about arrival directions? This is the sky map of significance of excess of neutrinos coming from different directions in the sky, reported as a p-value. If you know how to read this, what this is saying is there's no clear anisotropy anywhere in the neutrino sky. So there's no part of the sky that is emitting more neutrinos than another part of the sky, and there's no this significant dipole, quadrupole showing up over there. That doesn't mean there are no sources that we're discovering. There actually are sources, and it's super interesting, and I'm going to say more about this in a moment, but there's no obvious anisotropy in the neutrino sky. Pretty isotropic. And finally, about the flavors, I was saying that the pion decay toy model that I was showing earlier makes 2 mu neutrinos per each electron neutrino. That is the initial flavor composition. Neutrinos oscillate, they change their flavor from what they were produced with to something else. And if you account for those oscillations, then you no longer have the same proportion of flavor neutrinos at the Earth as you had at the sources. The oscillations change that along the way. Going back to our toy model of neutrino production, where we had, again, 2 mu neutrinos, so this one, and 1 electron neutrino produced in every pion decay. That we call it the full pion decay chain. And we say that there's 1/3 of the total flux is initially electron neutrinos, 2/3 is initially mu neutrinos, and we don't produce new taus. They need heavy charmed mesons to be produced, and we don't quite get the energetics of production for those in the sources. So we don't make new taus. So you might be familiar with this kind of ternary plots. Maybe if you work in particle physics, they kind of look like Dalit's plots. And what you're seeing here is that each axis is telling us what the amount of flavor in the incoming flux is. This is for electron flavor, muon flavor, and tau flavor. So each corner is a pure flavor. So this is a pure nu E flux, this is a pure nu mu flux, this is a pure nu tau flux. And points inside have coordinates whose sum adds up to 1 necessarily. All right, so this initial 1/3, 2/3, 0 flavor composition goes here in one of the axes. There's no new tau, so that's why it's on the axis. You turn on flavor oscillations along the way, and you end up at the Earth with something that is close to the center of a triangle. And by that, this is signifying that their expectation is we have about equal amount of nu E, of nu mu, and nu tau at the Earth. You can start from somewhere else at the sources, depending on the production process. For instance, if you have very intense magnetic fields, these intermediate muon will cool down by synchrotron emission, no longer make neutrinos of high energies upon decaying. So the only high energy neutrino you have is the one that comes directly from the decay of the pion, this one over here. So you start now with a pure nu mu composition at the very corner, turn on oscillations, and you end up at the Earth somewhere off to the left of the center. So you get a bit less electron neutrino flavors at the Earth. Or you can start from a different spot. You can start when you only have electron neutrinos to start with. That can happen, for instance, if you make neutrinos by beta decay, which only gives you mu E bars, and turn on oscillations, and then you end up on the opposite side. Okay, so this is our theoretical expectation for the flavor composition at the Earth. The canonical one, if nothing funny is going on, is that we expect about equal amount of each flavor at the Earth. And IceCube actually has the capacity, based on measurements of the number of showers. Remember, those are made by nu E and nu tau mainly, and the number of tracks, which are made by nu mus. IceCube has the capacity to infer what the flavor composition is from counting these two types of events. And what they have done is over the years, they have reported that flavor composition. This is from the first report that they had in 2015. This is the best fit that they get. No nu tau, that's why this best fit is over here. But look at the size of the 1 sigma, 68% containment region is huge. At the 2, 3 sigma, this is already filling the full triangle. And also it's very sensitive. The analysis is very sensitive to the data. And that's a bit of a trivial statement, but what I mean by that is that this was 2015, this is 2018, and you saw that the best fit moved from no nu tau to no nu E. So it jumped from one to the other. That means that the likelihood that they had is super flat. It's very difficult to measure flavor composition. But they continue doing it. And the last report that they had a couple of years ago now is moving closer to the center. Now the best fit is this purple star, and it's getting closer to our canonical expectation of equal amount of each flavor. But the size of the regions are pretty big still. All right. Okay, so far so good. The measurements are compatible with the standard expectations for the flavor composition, but the error bars are big. So, okay, so we're here today. And today, the thrust of the TeV to PeV neutrino side of things is to turn predictions that existed before the 2013 discovery of these neutrinos into data-driven tests. And some key developments that are going on today is that we're getting more events. We're building bigger detectors, improving reconstruction techniques. There's machine learning capabilities that are coming online in things like IceCube. And we are reducing the astrophysical uncertainties that allow us to understand the neutrino sources better. Okay, so based on that, let me just speak to what we have learned very quickly about astrophysics and what we have learned about particle physics with these IceCube neutrinos. So what have we learned about astrophysics? Our expectation is that neutrinos are produced in places where matter is very dense, so that the density of protons and the density of photons is high enough that they are likely to interact and make neutrinos by the process of pion production that I was showing earlier. There's essentially two candidates that come to mind, gamma ray bursts and blazars. And the mechanics of these at a very broad level are similar. So you have relativistic jets of matter and when that's spewed out by a central compact object. In the case of gamma ray burst, that has a Lorentz factor of about 100. In the case of blazars, that's about a Lorentz factor of about 10. But when the blazar is head-on looking at us, we can see the neutrino production reaching us at the highest energies. So what I mean by that is that down the line in the jet, you have collisions between places where there's under and over densities. And when the charged particles trapped in those collisions get accelerated at the shock fronts, they eventually undergo those proton-photon interaction processes and make neutrinos. If the jet is aligned towards us, the neutrinos that are produced actually are reaching us. So some of the ongoing searches for neutrino sources look at the catalog of known gamma ray bursts and the catalogs of known blazars and try to find correlations between the arrival directions of the neutrinos and the positions in the sky of these objects. And because gamma ray burst lasts a few seconds, this is very good because that means there's a little time for atmospheric contamination to affect our measurements. Blazars last for a longer period of time, so there the treatment is a bit different. IceCube has been looking for these correlations for years at this point, and I'm sorry to report that apparently none of these are the main sources of neutrinos. There are some caveats here. So the gamma ray burst contribution to the neutrino flux must be at most 1% of the flux that IceCube sees, and the blazars can contribute maybe 10, 20% of the observed flux at most. That doesn't mean that gamma ray bursts never make neutrinos. That doesn't mean that blazars never make neutrinos. It means that as a population, they're likely not the dominant ones making the neutrinos that IceCube is seeing. That said, we have seen one blazar making high neutrinos in 2017. A neutrino of 300 TeV of energy was detected by IceCube in coincidence with a flaring blazar, this TXS 0506 plus 056. Not only that, tidal disruption events, a completely different class of event, have also been associated with high energy neutrinos of lower energies, so tens of TeV or so. And late last year, the first steady state source of high energy neutrinos was reported by IceCube. And that's the active galactic nucleus known as NGC 1068 or Messier M77. It's a well-studied source, and we have about 80 events associated to this particular source. So it's a 4.2 sigma at this point, global significance association. So we are starting to have sources, and hopefully we'll have more in the next few years. But what have we learned so far in a bird's eye view? First thing we've learned is that the connection that I showed earlier between neutrinos, cosmic rays, and gamma rays is a lot more nuanced than we initially thought. So our initial expectation is that we see something that is bright in gamma rays, it should also be bright in neutrinos, because remember, gamma rays and neutrinos are produced by the same pion decay processes. That doesn't seem to be always the case. And the reason is maybe the sources that are good at having proton-photon interactions happen copiously are also too dense for gamma rays to be able to escape the sources. They Thomson scatter and they don't exit the sources at the PV the PV energies with which they're initially produced. So you get PV production of photons at the sources, they get reprocessed, and eventually they leave the source at lower energies. So MEV, not MEV, maybe infrared. That means that associating gamma rays and neutrinos with a particular kind of source might not be always the best idea. You need to look at a multi-wavelength view of these sources. Not only that, modeling sources is becoming more and more nuanced as well. There's nuclear cascades that happen when protons, actually heavier nuclei, interact with the sources, and that means that there is some imprint of the density profiles of the source inside the sources that will affect how many neutrinos are being made, because heavier nuclei will eventually photodisintegrate and give you lighter nuclei, and that affects how many neutrinos you can make. So that's also something that we're looking into. Okay, so what can you do in spite of all these uncertainties? I'm going to show you two examples. The first one is using neutrinos as magnetometers, and that means measuring the magnetic field intensity inside the sources by looking at the neutrinos that the sources could be making. And if we look at our original toy model, remember protons interact with photons, create pions, and then the pions decay into neutrinos. Protons and charged pions and the intermediate muons are charged particles. And that means that if the magnetic fields in the source where they exist are intense, they might cool by synchrotron emission. And if they cool, that means the shape of the energy spectrum of each of them changes. There are fewer neutrinos, fewer higher energy charged particles if they cool. And that imprints itself on the shape of the energy spectrum of the neutrinos that they make. So without going into a little detail, we do look for things like kinks and changes in the flavor composition that could be the result of these intermediate charged particles cooling by synchrotron emission. And because the amount of synchrotron emission that happens depends on the magnetic field intensity, the absence or presence of these features in the energy spectrum of the neutrinos can tell us about what the size of the magnetic field was at the sources. So if we do a full analysis using the neutrino events and look for these spectral kinks, we can actually say that even if we don't know what the source identity is for these neutrinos, we do know that whatever they are, they cannot have a super high magnetic field of 10 to the 4 Gauss or more. And that depends a little bit on how fast the production region of the neutrinos is moving inside the sources. Because if they had had such a high magnetic field, we would have seen these little kinks over here in the energy spectrum, which we have not seen. So that's one thing. We can use the neutrinos, to measure the magnetic fields at the sources. Something else we can do is try to look for specific features that are expected from broad classes of neutrino source candidates. So I was talking about neutrino production by proton-photon interactions. And I neglected to say one thing there, and that is that the neutrino energy spectrum coming from proton-photon interactions is actually bumpy. So it's centered around a certain characteristic energy that is given by things like the shape of the photon spectrum with which the protons are interacting with the source. That's for proton-photon interactions. For proton-proton interactions, the spectrum is actually like a power law, like I was saying earlier. So we can try to look into the data and see if the spectrum resembles more something that is bumpy from proton-photon interaction production of neutrinos, or something that is more like a power law, like you would expect from proton-proton interactions. So something bumpy, when I say bumpy, I mean something like this. The flux is a wide bump. It's not like very narrow, but it has a certain non-trivial width. So what we have done is gone and look into the data, current data, and try to see if there's evidence of any such bump at any energy on top of an underlying power law. Maybe there's proton-proton and proton-photon interactions making neutrinos at the same time, so they are contributing at some level simultaneously. And we're here, 2017. That's the last time IceCube put out a public release data that we have used for our analysis, and that this is the actual data points. Without going into a little detail, what I want to show you here is that we're looking for things like look like a bump, this red line on top of an underlying power law. There's no evidence, as you can imagine, because the error bars are pretty big, but this is quickly going to change in a few years once IceCube gets more data. Over here, once all the detectors turn on, I'm going to say more about these detectors in a moment, assuming these detectors have capabilities of neutrino detection similar to IceCube's, which is very reasonable, then in the future, these two hypotheses of separating a power law from proton-proton interactions from a bump-like spectrum from proton-photon interactions becomes a high precision endeavor. And that's going to happen in the next few years. Most of these, a big chunk of those detectors are actually being built today. So this is a realistic expectation. And then we can maybe tell apart whether the neutrino production process was mainly protons interacting with photons or protons interacting with protons. Okay, that's one part of the story. But as I was saying, the full story comes from looking at everything at the same time. So we've been talking about neutrinos. There's gamma rays and there's cosmic rays. And the full picture comes from the three of these messengers. And the fact that their energy spectrum is about at the same level should be, which is something we found in recent years after detecting neutrinos, should be evocative, or should be at least a hint of a possible common origin of these three messengers. Maybe like something akin to the toy model of neutrino, cosmic ray, and gamma ray production that I showed earlier. So I like films, and I like to think about this thing in the following way. If you remember Technicolor, these bright, very high contrast pictures, 40s, say 50s, 60s, 70s, Technicolor used different filters, and each one with a different wavelength, a different light, color, to give the total image once they were superimposed. So here it's a similar story. We have radio, infrared, and optical that gives us one part of the story. At higher energies, we have X-rays and gamma rays, which gives us more detail. Neutrinos gives us further detail, and gravitational waves completes the picture. So we have had one event that has given us at least most of the picture in such a way, and that is the GRB gravitational wave event, GW170817. And we saw it in gravitational waves. We saw it in lower energy electromagnetic emission. We didn't see it in neutrinos, but we saw it in high energy X-rays and gamma rays. Maybe the next one we will see neutrinos. So with that, we actually found out a lot of things about this multi-messenger emitter. And we got this, for me, it's one of the most beautiful pictures I've seen in the recent years. You see that this is the same event seen in gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, radio at the same time. If you add neutrinos, that's essentially the full picture. Maybe next time. Okay, so that's astrophysics. Now let me tell you quickly about particle physics, and that is all the host of different things I was showing in the beginning. And one way to think about them is to arrange them along two axes. And the first axis, this is just a bunch of my favorite beyond the standard model possible neutrino models at the highest energies. And you may see some of your favorite ones over there. We can arrange them along two axes. The first axis is where the models act in the lifetime of the neutrinos. They can act at the production stage, so in the astrophysical sources, or during propagation from the sources to us, or at the detector or inside the Earth. And each one of them can affect one of the four main high energy neutrino observables that I introduced earlier. So the energy spectrum, the Fibler composition, the energy spectrum, the arrival direction, the Fibler composition, and the arrival times. And these apparent mess actually speaks to the richness of the possibilities from the theory point of view on doing particle physics with neutrinos at the highest energies. And I'm not going to talk about all of them, but I will say one thing, and that is about measuring neutrino matter interactions at energies way beyond accelerator energies. What you're seeing there in the x-axis is, again, the neutrino energy, and the y-axis is the neutrino cross-section with protons or neutrons. And all these points over here are from accelerator neutrino experiments gathered over decades of different experiments, and some that are coming online in a few years. Okay, it stops at about 325 over here, and then with the new experiments, we can go up to, 325 GeV, and with new experiments, we can go up to the TeV scale. But beyond that, there is no accelerator neutrino experiments. We have predictions, of course, of what the cross-section should look like, and it continues to grow, not quite linearly, because there's the W pole that is messing that up, but it continues to grow slowly with energy. So here is where we can use IceCube and other detectors to measure the neutrino cross-section. So the way we do that is we use the Earth as a target and IceCube as a detector. And what we do is we take that isotropic neutrino flux that IceCube has been detecting, and we see what happens when the neutrinos at the highest energies propagate inside the Earth. There, neutrino matter interactions actually affect the amount of neutrinos that reach the detector from different directions. And that's because neutrinos inside the Earth, as they're propagating, may interact with matter, so neutrons and protons inside the Earth. If that interaction is via exchanging the W boson, then the final state lepton is a charged lepton, no longer a neutrino. If the interaction is via exchanging a Z boson, there's a final state neutrino of lower energy than the original neutrino. So the first process depletes the flux, is converting neutrinos into charged leptons. And the second process shifts the flux to lower neutrino energies. Okay, those two things we need to take into account when we do this propagation of neutrinos inside the Earth. We also need to know what the density profile of the Earth is. And we know this more or less from seismography. Okay, so here, the argument to measure the neutrino cross-section is to compare, as I said, the number of neutrinos that reach the detector from below after going through the Earth versus the number that come from above after just going through the atmosphere and maybe a little bit of dirt. Remember, IceCube is underground. If that, at low energies, the cross-section is, as we expect, low. So the number should be, the ratio of those numbers should be about 1. There shouldn't be much Earth absorption. But at high energies, that is no longer the case. And the ratio is now some function, an exponential function of the neutrino-nucleon cross-section. So by making this ratio, we can extract the cross-section. And that's what we did using the information from IceCube. And it turns out that we're able to measure the neutrino-nucleon cross-section for the first time at energies way past what an accelerator could do. Very well. So in my last 5 minutes, I'll say what's coming. And this, you should pay attention because it's something that is very close to what happens here at IAP. And this is what we have today. TeV to PeV neutrinos detected by IceCube so far. That's probably not going to be the case anymore in a few years. IceCube is getting bigger. It's called IceCube Gen 2. It's about 5 to 6 times bigger. But Antares is becoming KM3net. The Baikal detector is becoming a bigger Baikal detector, Baikal GBD. And there is a potential new detector about IceCube size in Canada. So now we don't only have, by the way, one neutrino. We will not only have one neutrino detector in the southern hemisphere, but also neutrino detectors in the northern hemisphere. And that gives us first sky coverage in case something happens somewhere else in the sky, not only where IceCube is most likely to see it. We might be able to catch it with a higher likelihood, but also we have a higher degree of statistics. And there are some efforts to combine all this information into a single framework and try to extract as much data as we can. That's one of them, Plenum. What happens at higher energies? Remember, these are the 1,000 PeV, the 10 to the 18 electron volt neutrinos we're talking about. These are the ones that we have not seen. And that's where things become interesting. That's the ultra high energy range that is untreaded ground. And we only have upper limits coming from IceCube, from the non-observation of those very high neutrinos, and from the Auger cosmic ray experiment as well. But there is a host of different neutrino telescopes that are targeting that new energy regime with different techniques and with different sensitivities. But I want to focus on 2 of them. That is IceCube Gen 2, as I mentioned earlier, and GRANT, which is a local, mainly local based, but also very globally distributed effort to build as good a sensitivity as possible, such that we might be able to discover these neutrinos, which expect to have very low flux. So the way these experiments work is they no longer see optical light. Now they look for radio emission from the same neutrino-nucleon interactions. So IceCube does it by looking at the radio emission inside the ice. There will be antennas buried in the ice, not as deep as the photomultipliers, maybe 100 meters or so at most. And GRANT does it by putting the antennas on the ground. And the principle is it's a bit different, but the advantage of using radio detection rather than optical detection is that radio attenuates a lot more slowly in space than optical light. And that means that you can instrument a larger volume of detector using fewer detection stations, in this case, fewer antennas. So this is something that is going on today. I'm involved in this. I've been involved in this for years with Olivier and Kumiko and people here at IAP and Peniche. And we're building out prototypes and deploying it in different parts of the world to test the detection principle and the stations. But okay, let's go back and see what we can do. So we have GRANT and we have Gen 2. And what are the fluxes? So the most naive thing is just to extrapolate what IceCube measured all the way to the ultra high energies. You see that at least for this one that is not too steep, we are on top of the sensitivity of these projected experiments and we might be able to detect neutrinos. This is a very naive expectation, by the way. We can do better. Remember, these neutrinos are made in the sources where proton interacts with the photons or the protons surrounding them, or along the way when cosmic rays interact with the CMB photons. So we can build models, flux predictions based on the cosmic ray interactions, either inside the sources or along the way. And we have done that. And we can normalize and find their parameters by making predictions of what the cosmic ray spectrum should be, comparing those predictions to the cosmic ray observations, and then inferring what the associated neutrino flux at the high energies should be. And of course, there's a lot of free parameters and knobs we can turn. And this is represented by the fact that the number of models is huge. And I'm just gonna flash them and I won't say much about them, but all of these are viable models of ultra high energy neutrino fluxes. And the breadth over here of several orders of magnitude is representative of the fact that this is the result of our highly uncertain knowledge of how ultra-high energy cosmic rays behave at the highest energies and what the sources are. So there are a number of things that are affecting our predictions, in particular how many sources there are at different distances, what is the mass composition of the cosmic rays at the highest energies, what is the maximum energies that the cosmic rays can reach, and therefore the maximum energies the neutrinos they make can reach, and a number of other things. Okay, so that speaks to the other thrust, the one that's looking into the next decade and to discover 100 PeV or more neutrinos. Today, we're making predictions for this new energy regime. The key developments here are discovery. That's what we want to do. We want to develop new detector technologies like radio detection because optical detection is no longer viable for such large volumes. And we're improving our flux predictions. So the situation today is more or less, and these should be made meaningful, these studies, by bringing in uncertainties from both particle physics and astrophysics. Otherwise, we'll be maybe misrepresenting our reach. So the situation for me is what cosmology looked like in the early 90s. And cosmology became quickly one of the highest precision fields in physics because data flooded it. And that happened over the 90s and still happens today. We are not at that stage with high energy neutrinos, but the goal is that as data comes in, as new detectors are built, as uncertainties in the predictions and in the measurements are reduced, where we might start to enter this high precision regime of testing. So today, what I try to do is tell you a bit about the music, but not the lyrics. So I've tried to give you a big picture of what's going on today and what could go on in the next few years realistically, of the efforts that are going on to get there today. But I didn't tell you about the details, and the details is where all the interesting stuff for me is. I'm very happy to answer those questions, but for now, thank you for your attention.
Thank you very much, Mauricio, for this excellent talk. Questions?
Great, thank you. But before you get into the details, I was struck by one of your latest plots where you compare the sensitivity curve to various models. And that was really clearly shows that there is a lot to be learned there and to be constrained. But on the other hand, yes, but I also noticed that IceCube Gen 2 is actually superior to GRAND on every single scale. So what is the reason to actually do GRAND? It's a simple question.
It is a simple question and a very valid one. Thank you. So the reason is they are actually, well, first, they're actually matching where things become interesting. This is where you have most of the constraining power between models. The energies between a few times 10 to the 8 and 10 to the 9. That's one thing. The reason is that they are going to be located in different places. And if you don't have, that's one first reason. If you don't have full sky coverage, you might not catch all the transient events that might happen in the sky. So essentially, if your detector is sitting in the southern hemisphere, because of the way these neutrinos are detected, you're mainly sensitive to transits that happen in the northern hemisphere and vice versa. Mm-hmm. So you need one in the southern hemisphere, like IceCube Gen 2, and then one or more in another place in the northern hemisphere. That's GRAND. That's one thing. The other thing is and I didn't show this in detail, but the angular resolution is an issue. And detecting neutrinos by radio in the ice is unclear how good the resolution is going to be. And by that, I mean, maybe for the best events, we can have 2 or 3 degrees of angular resolution on the point spread function. Mm-hmm. But that's a cut for the best events. But for most of them, it's probably going to be worse. And if you're trying to pinpoint sources, 2 or 3 degrees in the sky is huge. It's like saying there. Yeah, and then
and what is anticipated for GRAND in terms of angular resolution?
Yeah, so I'm coming to that. So for GRAND, because of the design of GRAND, it's expected that it's below 1 degree. probably 0.1 if we're good with it. And then it's not as good at things like radio, but it's certainly a lot better than 2 or 3 degrees. And that allows you to pinpoint sources better by different techniques like multiple detection or just catalog correlations. So one thing, again, sky coverage, which allows you to see more events. 2 is pinpointing accuracy. Those are the main reasons.
Are there some other aspects like control of systematics, or that, you know, not every experiment is ideal? So are there specificities that might be providing confidence if this is detected in 2 ways? Or, I mean, can you say a few more words on that?
Yeah, of course. I mean, think about LHC, right? That's what we have Atlas and CMS. They do the same but different. So there's of course commonalities, and the radio propagation in both in ice and in the atmosphere are different, but in the end, and it's the same charged particles that are emitting radio. There are different systematics for sure. Let's think about that one. So for instance, in Gen 2, you need to know the ice density well, because apparently when you're very deep in the ice, is the surface. As you go in depth, the density here is higher than the density here. So this is the deep and this is the shallow. And that means if you have a neutrino, a radio signal coming from a neutrino interaction, because of the gradient of the densities, radio does not propagate like this, but actually bends. Mm-hmm. So that doesn't happen in the atmosphere. So there are systematics that are different. You need to take into account of that, because otherwise you might misreconstruct the direction of the incoming. Mm-hmm. Certainly there are differences. And that's also true for the other experiments that I was showing earlier, the ones that don't even use radio. Some of them use Cherenkov emission from the upper atmosphere. Some of them use radar to test the particle showers in the atmosphere made by cosmic rays and neutrinos. All of them have different problems and different complementarities.
Is there an expected cost difference?
I'm not aware of what the latest numbers for Gen 2 are now, but my expectation is Gen 2 is maybe $100 million order US dollars experiment. Don't quote me on that. And grant, I believe, Kumiko, you might correct me, but it should be at the same level. So at least those 2 are comparable. The others, well, again, there's one that is a satellite experiment that is looking into the atmosphere from space. Just launching those is, $200, $300 million, just the launch. On top of that is the satellite. So there's a very large spread in cost. So which ones get built? Definitely the cheapest ones that allow you for the biggest sensitivity. Yeah.
Is it Chinese? This satellite is from whom?
No, it's US led. Yeah.
Can I just comment?
Yeah.
No, just about I think I'm not absolutely sure that they're confident about the sensitivity as well. IceCube Gen 2 radio. I mean,
they are pretty confident.
I mean, for the review with Fontini and Claire, we really iterated with them several times, and it wasn't very clear where they were sitting.
I know, so, but I'm involved in the technical design report.
Okay.
It's pretty much sits there.
Okay.
Now, whether they are going to be able to build it to the level of specification that they claim, that's a story. Yeah. But that's the same for everybody.
Yeah, as you said, actually. So we came up with Grand with the sensitivity limit like 5 years ago, because we wanted to be able to do astronomy of neutrinos, ultra-energy neutrinos. And all the experiments that came afterwards try to align to the sensitivity, because they couldn't claim to be not as good. So that became the benchmark. Yeah. And the angular resolution is really going to be, in principle, 0.1 degree. So that's fundamental. Yeah. Sorry.
Thank you for the very nice talk. Maybe I missed this, but in the list of future experiments, Ptolemy was not mentioned. I don't know if you can comment a bit on the progress on that front.
Yeah, so Ptolemy is an experiment that looks in the opposite end of the energy range. I don't think I have a plot of that, but you look at my plot, it's starting at 10 to the 6. Ptolemy is 7 orders of magnitude in the direction. So 0.1 millielectron volts. And that's looking for the relic neutrino background, the Big Bang neutrinos. So as far as I know, the initial prototypes of Ptolemy are either working or have worked. I don't know if they have been disassembled. And the way this works, and I'm not an expert on this, is you have essentially isotopes sitting there that are waiting to decay. So a relic neutrino comes in and prompts the decay, and then you see the recoil. The recoil is very faint because, again, we're talking about 0.1 electron volts. I believe that at least the initial stages of the experiment have been proven to be okay, but I don't know what their timeline is. I do believe they still plan to go ahead and build it. Yeah. And that would be, so I didn't say anything about low energy neutrinos, but of course, that's a whole different story that is super interesting as well. Yeah. Thank you.
More questions?
Thank you for this very clear and complete talk. But you mentioned that I saw the sterile neutrinos. How do you get constraints on sterile neutrinos in such experiments, or maybe on Majorana neutrinos? I don't know. Is there any possible? What are the possibilities?
So I was talking about these flavor oscillations, right? About the 3 neutrinos that I was talking about, nu E, nu mu, and nu tau. So the 3 of them can convert into one another. But if you have a 4th neutrino, let's say of KeV scale mass, then you can also maybe oscillate into that one. And so it's like a 4th flavor. And that would affect the proportion of the detectable neutrinos by the time that the flux of neutrinos reaches Earth. So it wouldn't be the 111 expectation of nu E, nu mu, and nu tau. It would be something different from that. It's a difficult test because the mixing parameters between active and sterile neutrinos have been constrained very stringently by oscillation experiments already. So the deviations that you can expect in the flavor composition of high energy neutrinos via these kind of experiments are actually pretty small. You might get bigger deviations, not from looking only at active to sterile neutrino mixing, but just in general non-unitary neutrino oscillations. And by that I mean there's 3 neutrinos traveling and interacting with a bath of extra degrees of freedom, and they're leaking into that bath. It might be sterile neutrinos, but it might not be. If it's not, then those strong constraints don't apply anymore. So bottom line, you use the flavor composition to test whether these neutrinos have leaked into something else. That's how you test sterile neutrinos.
Thank you.
Thank you.
Thank you for the very interesting talk. I have just two short questions. First, is there any constraint, at least, on the oscillation parameters, mixing parameters from high energies, especially from these 2 sources that you mentioned for TeV, PeV? And my second question, okay.
Let's start with that one. Yes. It's a very good question. Thank you. That was the hope back in 2010, for instance, and before the discovery of these neutrinos. There were papers written where you said, maybe if you saw a source of neutrinos at these high energies, you can constrain things like theta 1,3, one of the 3 mixing angles, maybe delta CP. In reality, the uncertainties in the flux are so big that they are not comparable to the precision you can get from oscillation experiments. The opposite is, usually what we do is the opposite. We inform our predictions using the knowledge of the uncertainty of the mixing parameters measured by oscillation experiments. That informs our regions of flavor composition high energies. That definitely happens. You can still test flavor changing oscillation physics at the highest energies with these, but that's when you add an extra thing on top of the normal oscillations. So it's not about, in that case, it's not about measuring the normal oscillation parameters. It's about measuring new stuff that affects oscillations. Unfortunately, the precisions are not good enough. If you go down in energy a little bit and you use atmospheric neutrinos, not astrophysical neutrinos, then yes, you can measure oscillation parameters very well with those, even with IceCube, which also takes atmospheric neutrinos.
Thank you.
I can. So you can have a C prime that interacts with the neutrinos, and that connects neutrinos with quarks, but unlike the new normal Z from the standard model, this is flavor changing. So you can have couplings that are flavor dependent. Yeah.
Hi, yeah, very nice talk. You showed the distribution of neutrinos on the celestial sphere and said that it was uniform, but it didn't look uniform to me.
It's because
the northern part, there's no detections. Is that because you're going through the Earth?
Let's show it again so we are all on the same page. I think you meant this.
Yep, that's not uniform to me.
It is not. But you have to look at the scales and what these numbers represent. This is a test statistic. So okay. This is not number of events.
Okay.
This is the significance of the excess across different directions in the sky. And the darker the spot, the higher the significance of the background of atmospheric neutrinos. So the darkest spot is over here, and that has a p-value post-trial of 0.092. That means that this is likely just an atmospheric neutrino background fluctuation. That's what it means. If you wanted to see what this looks not in excess p-value sky, but in actual events, then that's more or less this map.
Okay.
So these are actual events, and then you're absolutely right. So this is now in galactic coordinates, and the Earth North Hemisphere is this region over here. And then you see fewer events here than in the South Hemisphere. And the reason for that is that neutrinos coming from the North Hemisphere have been absorbed by the Earth. When you do this anisotropy analysis, like the one in the other plot, you need to undo or correct for the absorption effects. And yeah.
Okay, thanks. Great. Just one very last question. Then you said that the neutrinos were 10% blazars, 10% gamma ray bursts. Yeah. But what's the rest then? Okay.
Yeah.
Okay.
So
thanks. Thanks for that.
Okay, over the past 2-3 years, there's been papers actually trying to figure out what the percentage contribution of different source classes could be by looking at associations with different catalogs. And it might just be that we live in a world where there's a cocktail of things. So we have some of it is made by blazars, some of it is made by superluminous supernovas, some of it is made by maybe GRBs, starburst galaxies, etc. And the percentage is more or less comparable among all of them, at least in this very initial study. So tens of percent. Yeah, thank you.
More questions? One more. The last one, I think.
Concerning the detection technique, if I understand it so far, it's based on Cherenkov radiation through water. Have there been any other type of detection techniques for neutrinos other than Cherenkov radiation?
I mean, sure, yes. The ones, I have to say, currently the large-scale neutrino telescopes like IceCube work only by Cherenkov detection. But there have been explorations of using, for instance, acoustic detection. So neutrinos do make pressure waves when they interact. I believe that was more or less abandoned a few years ago, and I've seen some resurgence in the past couple of years, so that might be something that I'm looking into again. For this energy range, optical is the best bet. It's easy to instrument a volume that you would need to detect a flux like the one IceCube is looking at. For the ultra high energy range, that's no longer true, and that's why I was talking about radio. But as I said, there's also Cherenkov light in the atmosphere. That's when the neutrinos interact not in the ice, but like in the upper atmosphere. There's, for instance, if a neutrino or a cosmic ray as well interact in the atmosphere, it creates a particle shower. You can also think about having a radar. So you emit radar, that radar bounces off and you detect it over here. And it depends on the bouncing, you can measure things about the shower parameters. So that's another technique based on radio, but not really the same way as Gen 2 or GRAND. You can think about just imaging telescopes that's also being used. Or you can think about Pierre Auger, and Auger detects the particles themselves as they reach the ground level. All of them are more or less complementary. Yeah, thank you.
Okay, I think we should thank again Mauricio